Long before satellites traced every coastline, people believed the sea could be understood by watching it. They learned the rhythm of waves. They memorized the color of approaching storms. They trusted that danger would announce itself in wind, cloud, or sound. In the Atlantic, it often does not. This ocean has claimed more human lives than any other on the planet. Ships vanished here before radios could speak for them. Others disappeared after technology promised connection. Some voices broke off in the middle of ordinary sentences. Many were never heard at all. Across the Atlantic floor, wreckage does not rest in neat isolation. Vessels lie layered one atop another, pressed into canyons, buried in shifting mud, or scattered across ground that should be still. Some appear far from any current capable of carrying them there. Others seem to fade again after being found, as if the ocean refuses to keep a fixed record. The ground itself is not secure. Entire sections of seafloor can slide slowly, silently, collapsing canyons and altering depth in ways ships above cannot detect. There is no sound, no shaking, only the moment when the water begins to rise where it should not. Far deeper still, the Atlantic is unfinished. A long fracture in the earth continues to pull the ocean apart, creating new seafloor while other parts sink and disappear. Some trenches have existed longer than recorded history. Others are still forming now, out of sight. But why does this ocean contain more recorded shipwrecks than any other on Earth? What allows vessels to appear far from where currents and charts say they belong? And what else has been taken into depths that continue to change? Tonight, we drift softly across water that seems calm, while the world beneath it continues to move. But before we begin, I would love to know where in the world you're listening from and what the time is there. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle journeys into the mysteries of our oceans, please do consider leaving a like and subscribing to the channel. Now take a deep breath, close your eyes, let your shoulders soften, and let's begin. The Atlantic did not arrive fully formed. It emerged quietly, through patience and strain, while the surface of the planet rearranged itself in slow motion. Long before waves traced its margins, all the familiar continents were pressed together into a single immense body of land. Forests stretched across regions that would one day face opposite horizons. Rivers crossed ground that had not yet learned separation. Beneath that vast landscape, heat accumulated, pressure built, and stone began to soften in ways invisible from above. The crust holding that supercontinent together did not fail suddenly. It thinned first, it warmed, it stretched like fabric under steady weight. Small fractures opened deep below, allowing molten rock to rise and cool, adding new material where the earth was pulling itself apart. These narrow rifts lengthened over millions of years, widening just enough to admit water from the surrounding seas. Each intrusion was modest, but together they marked the beginning of an irreversible change. What would become the Atlantic started not as an ocean, but as a narrow scar, breathing heat and steam into shallow basins. As the land continued to separate, the opening grew wider. Seafloor spread outward from a central seam, cooling as it moved, growing heavier, and slowly sinking beneath its own weight. Coastlines formed where none had existed before. Shallow shelves replaced once continuous plains. Water crept inward, filling low places and carrying sediments that buried the memory of what had come before. The Atlantic expanded patiently, its edges inching away from one another, year after year, century after century, until it was no longer a passage but a basin. Compared to older oceans, its age shows. The Pacific carries scars from a much earlier world, crust so ancient it has been folded, broken and recycled beyond recognition. The Atlantic, by contrast, still displays its construction lines. Much of its floor remains relatively young, its rocks thinner, warmer, and closer to the restless interior beneath. Heat escapes more easily here. The boundary between solid ground and molten depth sits nearer to the surface, lending the entire basin a quiet instability. This youth shapes how the Atlantic behaves. Its seafloor is not settled into long equilibrium, but remains in motion, slowly spreading, adjusting, and slipping. New crust is continuously born along its central spine, while older sections cool and sink at the margins. These movements are gentle on human timescales, yet persistent enough to reshape the environment in subtle ways. Slopes shift, sediments pile unevenly. Entire sections of seabed may give way under their own weight, sliding silently into deeper water. Above this restless foundation, the ocean responds. Depths vary abruptly. Currents encounter unexpected contours that redirect their flow. Pressure changes are uneven, shaped by ground that has not yet finished forming. The Atlantic's relative youth leaves it less predictable, its structure still negotiating the balance between creation and collapse. It is an ocean learning its own shape, while already carrying the weight of history upon it. From space, its surface appears smooth and coherent, a single expanse of blue. Beneath that calm exterior lies a basin still under construction, shaped by processes older than memory, yet young by planetary standards. The Atlantic exists in motion, not as a finished feature, but as an ongoing transformation. Water fills a space that is still being made, drifting over ground that continues to stretch, cool, and slip, quietly reminding the planet that some boundaries are never truly fixed. Far below the Atlantic's surface, beyond light and current, the seafloor rises into a vast spine that runs almost the entire length of the ocean. It does not stand like a single wall or peak, but as a continuous chain of ridges, valleys, and broken heights stretching from the northern reaches toward the far south. This underwater range is longer than any mountain system on land, yet it remains unseen by those who cross above it, hidden beneath kilometers of moving water and pressure. Along this submerged backbone, the Earth remains quietly active. Heat from deep within the planet travels upward, carried by molten stone that moves slowly through cracks in the crust. When it reaches the surface, it cools almost instantly, hardening into new rock as it meets the surrounding cold. Layer by layer, the ocean floor is built outward from this central line. What forms here is not ancient ground but fresh terrain, still warm at its core, still adjusting to the weight of the water above. The ridge is not smooth or symmetrical. Its surface is torn by fissures, offset by fractures, and reshaped by subtle shifts that never fully stop. Valleys open where the crust stretches thinner. Ridges rise where new material accumulates. In some places, the seabed splits enough to allow warm fluids to seep through, carrying dissolved minerals that bloom into slow-growing structures before drifting away into darkness. These movements happen without sound, without tremor that can be felt above, yet they continue day after day, reshaping the basin from below. As new seafloor forms, older ground is pushed outward on either side, cooling as it travels. Over time, this rock grows denser and heavier, settling lower into the mantle beneath. At the far edges of the ocean, parts of this aging crust eventually bend downward and slip away, returning to the depths from which they came. Creation and disappearance occur together, balanced across immense distances and spans of time. The Atlantic's floor is never entirely finished, nor entirely erased. This constant renewal gives the ocean a distinctive structure. Heat lingers closer to the surface along the ridge, warming the waters above and subtly influencing how currents rise and fall. The seabed nearby is uneven, marked by sudden drops and unexpected elevations that redirect movement through the deep. Sediments slide into newly formed valleys, while older layers fracture and shift under slow stress. Even without violent motion, the ground remains in negotiation with itself. Life has learned to exist within this quiet activity. In places where warmth escapes into the cold abyss, small ecosystems take hold, drawing energy from chemical reactions rather than sunlight. Creatures gather where the earth exhales, living briefly on ground that did not exist in the distant past and may not last far into the future. The ridge provides both foundation and impermanence, offering space while quietly reminding everything above it that the surface is borrowed. From the surface, the Atlantic appears stable, its waves repeating familiar patterns. Beneath that surface, the mid-Atlantic ridge continues its patient work, extending the ocean a fraction at a time, reshaping the depths grain by grain. The water above drifts on a floor that is being written and rewritten, carried forward by a mountain range that never stops growing, never fully settles, and never truly sleeps. The Atlantic does not rest within its boundaries. Even now, long after coastlines have been drawn and named, the ocean continues to widen in almost imperceptible motion. Each year, the continents edging its shores move a little farther apart, carried slowly by forces that never pause. The change is too small to notice in a lifetime, yet over ages it reshapes distances, deepens basins, and alters the balance beneath the water. This widening happens quietly along the ocean's central spine, where new ground forms and pushes outward on both sides. As fresh seafloor cools and settles, it makes space for the Atlantic to expand, fraction by fraction. The surface above remains familiar, but the foundation below stretches like a slow breath held over millions of years. It is an ocean growing not through sudden floods, but through steady persistence. With this growth comes subtle instability. As the crust moves, it does not slide smoothly like polished stone. It grips, strains, and releases tension in gentle adjustments and occasional slips. These shifts can send ripples through the surrounding rock, small rearrangements that rarely announce themselves at the surface. The Atlantic carries these movements within its depths, absorbing them beneath layers of water and sediment while continuing to spread. In some regions, the seafloor responds by tilting or settling unevenly. Slopes change their angle. Sediments that once rested securely begin to creep downslope, drawn by gravity and the slow reshaping of the ground beneath them. These movements are patient and nearly silent, unfolding over years or centuries. Above, ships pass unaware, their paths tracing calm arcs across water that hides steady transformation below. The energy released by shifting crust can sometimes travel far from its source. Earthquakes born deep beneath the ocean floor may never break the surface, yet they can subtly rearrange the seafloor. Faults adjust their position. Layers compact or fracture. Channels open where currents find new routes. The Atlantic accepts these changes without interruption to its rhythm, its surface repeating familiar patterns even as its structure changes. This ongoing motion creates hidden challenges in the deep. Areas that appear stable on maps may slowly alter their depth. Ridges rise by small increments, while basins sink further under accumulating weight. Sediment can pile unevenly, masking hard edges and concealing sudden drops. Over time, what was once a gentle slope may become a fragile ledge, ready to give way under the right conditions. For anything resting on the seafloor, permanence is uncertain. Cables stretch across ground that shifts beneath them. Wrecks settle into mud that continues to move, sometimes tilting or sinking as the layers below adjust. Channels carved by currents deepen or migrate, carrying material away from places that once felt secure. These changes unfold without urgency, yet they never stop. The Atlantic's growth is a reminder that oceans are not static containers, but evolving spaces shaped from below as much as above. Water fills a basin that continues to widen, deepen, and reorganize itself, guided by forces older than the surface world. While winds and waves write fleeting patterns overhead, the true expansion happens in silence, far beneath the reach of light. This slow widening does not demand attention. It continues regardless of observation, measured in distances too small to sense and times too long to witness directly. Yet it leaves its imprint everywhere, in the shifting floor that supports the ocean and the quiet instability that lingers beneath passing ships. The Atlantic grows not with drama, but with patience, carrying its changes gently forward into the dark. As the Atlantic deepens and cools, the water takes on a different role. Far below the shifting surface and restless currents, temperature becomes the quiet architect of preservation. Cold settles into the depths and remains there, heavy and unhurried, pressing against everything that falls into its reach. In this environment, time does not move as it does above. It slows, stretches, and becomes something almost physical. Cold water changes the chemistry of decay. The processes that break down living tissue and worked materials rely on warmth, motion, and oxygen. In the deep Atlantic, warmth is absent. Movement is minimal. Oxygen thins as depth increases, limiting the activity of organisms that would otherwise consume what arrives from the surface. What remains is a stillness that interrupts the usual rhythm of dissolution. Bodies that sink into these depths enter a space where biological urgency fades. Bacteria work more slowly. Scavengers arrive late, if at all. Soft tissue persists longer than expected, protected by low temperatures and crushing pressure that discourages disturbance. Over time, minerals seep in, replacing what was once organic, creating forms that hover between life and stone. The Atlantic does not erase quickly here. It holds. Ships experience a similar pause. Wood swells, then stabilizes in the cold. Steel corrodes at a gentler pace, its reactions slowed by the absence of warmth and light. Without waves to batter them and storms to grind them apart, hulls rest in quiet balance. Decks remain aligned, cabins stay enclosed. Objects lie where they fell, as if hands have only just let go. Sediment plays its part as well. Fine particles drift downward and settle slowly, wrapping wrecks in thin layers that protect them from currents. This covering can seal gaps, reduce exposure, and create pockets where water barely circulates. In these sheltered spaces, decay slows even further. The ocean floor becomes an archive, stacking material gently rather than scattering it. This preservation gives some wrecks an unsettling clarity. Plates remain stacked, shoes stay paired, instruments rest where they were set down. The impression left behind is not of collapse, but of interruption. Motion ceased, and the environment accepted that stillness. The Atlantic does not recreate the moment, yet it allows its outline to persist, carried forward in cold silence. Not all wrecks share the same fate. Where currents are stronger or chemistry differs, destruction continues at a faster pace. Iron-eating microbes thrive in certain conditions, consuming steel with steady determination. Wood can be stripped away where oxygen flows freely. The Atlantic holds multiple climates within itself, and preservation is unevenly granted. Some sites endure like sealed rooms, while others fade until only shadows remain. Even so, the cold remains a dominant influence. It governs vast stretches of the deep, shaping how long traces endure and how clearly the past can be seen. In these regions, the ocean floor becomes a place where decades blur together, where materials outlast expectation. The cold does not freeze time completely, but it softens its passage. What lies preserved is not untouched. Pressure compresses, minerals infiltrate, and slow change continues beneath the surface of stillness. Yet compared to the constant renewal above, the deep Atlantic offers patience. It keeps what it can, quietly adjusting it to fit a colder world. In this layered darkness, the ocean carries fragments of human history and natural form alike, resting within water that rarely warms and rarely stirs. The cold does not return what was lost, but it resists erasing it. Here, the Atlantic remembers by slowing everything down, allowing outlines to linger long after motion has ceased. Across the Atlantic, movement is rarely random. Beneath the surface, immense rivers of water travel with steady purpose, guided by Earth's rotation, temperature contrasts, and the shape of the ocean basin itself. These currents do not rush. They flow with endurance, carrying warmth, cold, salt, and memory across thousands of kilometers, linking distant regions into a single circulating system. Near the equator, sunlight pours into the ocean, warming surface waters until they grow lighter and begin to travel. This warmth is gathered and drawn northward along the western edge of the Atlantic, forming a powerful current that moves like a slow tide with direction. As it travels, it releases heat into the air, softening climates far from the tropics. Coastlines feel its presence through milder winters and lingering warmth carried on damp winds. The water cools gradually as it goes, giving up energy without ever truly stopping. Farther north, this flow spreads and bends, becoming part of a wider drift that crosses the open ocean. Here, warmth disperses into colder regions, thinning and sinking as temperatures drop. The water grows heavier and begins its descent, slipping beneath the surface to begin a return journey that may take centuries. This continuous exchange of rising warmth and sinking cold helps regulate the planet's climate, redistributing energy in a slow, deliberate cycle. Within this system, the Atlantic becomes a conveyor rather than a container. Heat moves poleward, cold returns toward lower latitudes, salinity shifts, influencing density and depth. These layered movements create invisible highways beneath the waves, each traveling at its own pace and depth. Some currents skim the surface, brushed by wind. Others crawl along the seafloor, guided by pressure and temperature rather than air. When ships descend into this moving water, they enter a dynamic environment that rarely leaves anything in place. A vessel may sink through one current and come to rest in another, its descent shaped by layers that drift in different directions. As debris separates, lighter materials can be carried far from the initial site, spreading outward in slow arcs. Even heavier structures may be nudged over time, guided by persistent flow rather than sudden force. Along the bottom, deep currents continue their work. Cold, dense water slides through channels and over subtle slopes, capable of moving sediment grain by grain. Wrecks resting on these paths may shift gradually, inching downslope or rotating as currents find new routes around them. Over years, what sank in one place may no longer be found directly beneath that point. The movement is gentle, yet constant. These currents also reshape the seafloor itself. Sediments are swept from exposed areas and deposited elsewhere, burying some sites while uncovering others. Channels deepen where flow concentrates. Ridges accumulate fine layers that settle quietly from above. The map of the deep Atlantic changes without urgency, altered by water that never truly rests. Above, the surface reflects a simpler story. Waves rise and fall, weather comes and goes, and routes appear predictable. Below, the currents continue their long circulation, indifferent to borders or timelines. They link equatorial heat to polar cold, surface motion to abyssal stillness, and distant places into a shared system. Through this steady movement, the Atlantic exerts influence far beyond its shores. It shapes climates, redirects sinking ships, and rearranges what lies on its floor. The water carries energy, matter, and time itself, flowing onward with quiet persistence. In this slow circulation, the ocean reveals itself not as a static expanse, but as a living network of motion that reaches into every layer of the world it surrounds. Within the Atlantic, there is a region where orientation becomes less certain and patterns feel subtly unsettled. Here, the forces that guide navigation do not align as neatly as they do elsewhere. The planet's magnetic field, usually reliable, shifts its angle across this zone. Compasses do not point toward a single fixed reference, but vary slightly depending on position, depth, and time. These variations are not dramatic, yet they are persistent, creating small discrepancies that accumulate quietly over distance. Magnetic lines drift across the region like invisible contours, shaped by the structure of the Earth beneath the ocean. Differences in crustal composition influence how magnetic signals pass through, bending them just enough to challenge expectation. For experienced navigators, the change demands constant awareness. For instruments, it introduces room for interpretation. Direction remains available, but certainty softens at the edges. Above the water, the atmosphere adds its own complexity. Warm air rising from the ocean surface meets cooler layers descending from higher altitudes, and where these masses converge, weather can organize itself quickly. Storm systems may form with little warning, growing from scattered clouds into structured winds in a short span of time. Rain can fall heavily in narrow bands, while neighboring waters remain calm. Visibility shifts, horizons blur, and familiar cues lose their clarity. This rapid weather formation does not rely on distant fronts. It emerges locally, fed by warm currents and unstable air, building upward and outward before dispersing again. For those traveling through, the transition can feel abrupt. Skies change tone, winds redirect. Navigation that once depended on visual references must adjust to motion and sound alone. Below the surface, the seafloor drops away sharply. Plateaus give way to steep slopes, and shallow shelves end suddenly in deep water. These drop-offs alter how currents behave, accelerating flow and creating vertical movement where water sinks or rises along the edges. Waves passing above can stack in unusual patterns, interacting with water pushed upward from below. The sea may appear uneven without obvious cause. These depth changes also influence navigation systems that rely on pressure and depth awareness. Instruments calibrated for gradual descent encounter sudden absence beneath them. Signals reflect differently off steep walls than they do from flat seabed. Sonar readings stretch or compress, requiring interpretation rather than simple measurement. The ocean here does not offer uniform feedback. When these elements combine, magnetic variation, rapid weather shifts, and sudden depth changes, navigation becomes an exercise in adjustment. Small errors compound gently. A course set with slight imprecision drifts farther over time. Wind alters progress. Currents redirect paths below the surface, unseen yet persistent. What begins as a minor deviation may not announce itself until distance makes correction more difficult. Human navigation has always depended on patterns. Stars, compasses, coastlines, and later satellites provide a sense of order. In this region, those patterns overlap imperfectly. Signals disagree by small margins. References shift. Trust moves from certainty to continuous recalibration. The environment does not remove guidance, but it requires attention at every moment. The science behind these conditions is layered rather than singular. No single force dominates the region. Instead, subtle influences gather and interact, shaping behavior without spectacle. The ocean floor falls away. The air reorganizes itself. The magnetic field bends slightly from expectation. Each factor alone remains manageable. Together, they create a space where direction must be earned rather than assumed. In this convergence, the Atlantic reveals one of its quieter complexities. It does not deceive through illusion, but through overlap. Forces align imperfectly, and navigation unfolds within those imperfections. The water moves onward, carrying currents, signals, and weather through a region shaped not by mystery, but by the delicate balance of natural systems working at once. Over the Atlantic, storms begin without ceremony. They start as quiet disturbances, small gatherings of heat and moisture rising from the ocean's surface. Warm water releases energy steadily into the air above, lifting it higher and higher in slow, invisible columns. As this air rises, it cools slightly, allowing moisture to condense into clouds that stretch upward, pale and unassuming at first. The Atlantic provides an unusual abundance of warmth for this process. Vast stretches of its surface absorb sunlight and hold it, especially across tropical and subtropical waters. Heat penetrates deep enough to remain available even as winds stir the upper layers. When conditions align, this stored energy begins to organize. Air flows inward toward the rising column, drawn gently at first, then with growing cohesion. Rotation follows, shaped by the planet's spin, giving the system a sense of direction. As the storm gathers strength, its structure becomes more defined. Bands of cloud curve around a forming center, lifting more warm, moist air from the sea below. Each cycle feeds the next. The ocean responds by releasing more heat, reinforcing the upward motion and lowering pressure near the surface. This exchange between sea and sky is continuous, a quiet conversation carried out over hours and days. Warm water acts as fuel not through violence, but through consistency. It sustains the storm by preventing the rising air from collapsing back downward. As long as the system remains over warm regions, energy continues to flow upward and the storm grows broader and taller. Clouds climb higher into the atmosphere, winds stretch outward. Rain becomes more organized, falling in sweeping arcs that extend far from the center. The Atlantic's open space allows these systems to mature without interruption. With long distances between landmasses, storms can travel for days while continuing to draw energy from the surface below. Their paths curve gently, guided by global wind patterns rather than immediate obstacles. From above, they appear as slow spirals, elegant in form despite the power they carry. For ships, this development can unfold with unsettling speed. A vessel may begin its journey under ordinary skies, surrounded by modest swells and steady wind. Hours later, the same waters can become crowded with rising waves and shifting currents. Winds strengthen, pushing against hulls with growing insistence. Swells lengthen and steepen, stacking rhythm upon rhythm until the sea no longer offers predictable motion. As the storm tightens, waves interact with one another, creating uneven surfaces that strain navigation. Rain reduces visibility, blending sea and sky into a single muted field. Compasses and instruments continue their work, yet the environment around them changes faster than plans can adjust. What was once a distant weather system becomes an immediate presence. The danger lies not only in height or wind, but in duration. Hurricanes carry energy that does not disperse quickly. They maintain their structure over vast distances, applying sustained pressure to everything in their path. For ships caught within their reach, escape becomes difficult. Progress slows as waves resist forward motion. Maneuvers demand constant correction. Hours stretch longer as conditions compound. Beneath the surface, currents respond as well. Warm water is drawn upward and outward, while cooler water rises to replace it. This movement reshapes the sea's internal layers, adding to the complexity above. The Atlantic becomes a fully engaged system, air and water responding together in layered motion. When storms finally weaken, they do so gradually, losing access to the warmth that sustained them. Their energy dissipates and their structure loosens, yet the water remembers. Waves travel far beyond the storm's center, carrying its influence outward across the ocean, long after skies clear. In this way, the Atlantic serves as a birthplace rather than a battleground. Storms emerge from simple exchanges of heat and motion, shaped patiently by water and wind. They grow not through sudden chaos, but through steady reinforcement, unfolding across an ocean that quietly provides the conditions for their rise. Out in the open Atlantic, far from shore and routine patterns, the surface can change in ways that resist expectation. Most waves arrive as part of a rhythm, rising and falling in familiar sequences shaped by wind and distance. Rogue waves belong to a different category. They are not extensions of the surrounding motion, but brief departures from it, walls of water that gather height without warning and then disappear back into the sea. These waves have been recorded with clarity. Instruments fixed to platforms and satellites passing overhead have measured single crests rising far above the surrounding swell, reaching heights comparable to tall buildings. Sailors have reported encountering them long before such measurements existed, describing moments when the horizon itself seemed to lift. For centuries, these accounts were treated as exaggeration, yet the data now shows that such waves are real, rare, and sudden. Their formation does not rely on storms alone. Rogue waves often emerge in conditions that appear otherwise ordinary. Wind waves traveling at different speeds can overlap, their energies aligning briefly into a single peak. Currents moving against wave direction can compress energy into a smaller space, forcing water upward. In certain regions of the Atlantic, shifting currents and uneven depths encourage this convergence, creating places where motion stacks rather than disperses. Timing plays a role as well. When multiple wave systems intersect at just the right moment, their crests add together instead of canceling out. This amplification lasts only seconds, but during that brief alignment, water can surge upward with extraordinary force. Once the interaction passes, the energy redistributes, and the ocean returns to its previous state as if nothing unusual occurred. To an observer at sea level, this transition offers little warning. A ship may ride steady swells when a much larger mass of water suddenly rises ahead, steep and nearly vertical. There is no gradual buildup. The wave arrives already formed, carrying momentum that has been concentrated across many kilometers of moving water. The danger lies in both height and shape. Rogue waves tend to be steeper than ordinary waves, presenting a near wall rather than a rolling crest. When such a wave strikes a vessel, the force is delivered all at once. Hulls designed to withstand pressure from below may be struck broadside or head-on by water moving faster than expected. The impact can overwhelm structural limits in moments. Large ships, often assumed to be immune due to their size, are not exempt. The mass of a rogue wave can flood decks, damage superstructures, and destabilize balance almost instantly. Water entering compartments shifts weight suddenly, compromising stability. In severe cases, the force alone is enough to cause catastrophic failure before corrective action is possible. What makes these waves particularly unforgiving is their isolation. They are not accompanied by a sequence of similar crests that allow adjustment. There is often only one. After it passes, the sea may settle back into its previous pattern, leaving little visible trace of what occurred. Survivors describe a sense of abrupt interruption, where normal motion was replaced briefly by something immense and singular. Beneath the surface, the energy that produced the wave continues onward, dispersing into currents and deeper layers. The ocean absorbs the event without pause, folding the movement back into its ongoing circulation. No scar remains to mark the location. Rogue waves remind us that the Atlantic does not always express its power through prolonged storms or visible systems. Sometimes it concentrates its energy into moments too brief to predict, shaped by layers of motion aligning just once. In those seconds, the familiar surface gives way to something taller, heavier, and decisive, before quietly returning to its steady, drifting calm. Beyond the shifting surface and busy currents, the Atlantic falls away into places where depth becomes the defining presence. The ocean floor does not descend evenly. In certain regions, it bends sharply downward, opening vast depressions that stretch far below the surrounding seabed. These trenches are not wounds in the earth, but expressions of slow, patient force acting over immense spans of time. One of the deepest of these descents lies north of the Caribbean, where the seafloor curves into a long, narrow basin. Here, the crust has been pulled, bent, and pressed downward as massive plates interact beneath the water. The Atlantic, though younger than other oceans, carries areas where the ground yields dramatically, allowing depth to accumulate layer upon layer until the surface world feels distant beyond measure. This downward drop begins gradually, then steepens. Gentle slopes give way to sharper angles as sediment thins and rock is exposed. Gravity draws loose material downward, creating smooth walls interrupted by terraces where movement has paused for a time. Over ages, these surfaces are reshaped again and again, not by sudden collapse, but by persistent weight pressing from above. The reason for these extreme depths lies in the balance of forces beneath the ocean. Along certain boundaries, the seafloor is forced to curve downward as denser crust sinks relative to lighter sections nearby. The rock does not fracture violently, it bends, yielding inch by inch under pressures that never relent. What forms is a trench that grows not through rupture, but through surrender to gravity and heat. As depth increases, pressure becomes the dominant condition. With every descent, the weight of water multiplies, bearing down with steady intensity. Objects falling into these regions encounter a change that begins subtly and becomes absolute. Air spaces vanish quickly as pressure compresses them out of existence. Materials behave differently. Wood that once floated becomes heavy. Steel grows vulnerable, its strength tested by forces acting from every direction at once. For living tissue, pressure reshapes what remains. Gases dissolve, structures compact. Forms that were familiar above are altered into denser versions of themselves. Movement slows as water thickens in effect, resisting motion more strongly at depth. Nothing here escapes transformation. Everything adapts or it settles into stillness. Light cannot follow far into these trenches. Darkness arrives long before the bottom does, leaving the descent guided only by instruments and gravity. Sound behaves differently as well, Traveling in elongated paths and reflecting unpredictably off-sloping walls, the sense of space changes. Depth ceases to feel like distance and becomes a condition, something that surrounds rather than separates. Despite this severity, these trenches are not empty. Life persists in forms shaped by pressure and scarcity, existing within the narrow tolerances allowed by the environment. Movement is minimal. Energy is conserved. The trench becomes a quiet corridor where survival depends on patience rather than speed. For ships and objects that reach these depths, the outcome is final. The journey downward ends in a place where retrieval is impractical and observation remains limited. What settles there joins a realm governed less by motion than by compression and time. The Atlantic does not recycle these depths quickly. It accepts them as endpoints. In these deepest reaches, the ocean reveals a different scale of existence. The surface world continues above, animated by wind and weather, while far below, trenches hold space where the planet's weight is fully felt. Here, the Atlantic stretches downward into silence, carrying everything that arrives into a pressure-shaped stillness that resists return. When the great liner slipped beneath the Atlantic, it entered a world designed to conceal rather than reveal. The descent was long and uninterrupted, carrying the ship into darkness where temperature and pressure reshape everything that arrives. Once it reached the deep, the ocean did not announce its presence. It simply closed around the wreck and began the slow work of separation from the surface world. The location itself played a role in the long absence. The Atlantic floor where the ship came to rest is vast, uneven, and difficult to survey. Depth absorbs sound and light, turning exploration into a process of careful listening and patient mapping. For decades, technology was limited to short glimpses and narrow paths, and the wreck lay beyond reach, surrounded by miles of water that softened signals and scattered echoes. The ocean did not hide the ship deliberately. It offered space enough for it to remain unseen. As the years passed, the deep Atlantic shaped what remained. Cold surrounded the hull immediately, drawing heat away and slowing chemical reactions that would have progressed more quickly nearer the surface. The water there is calm, shielded from waves and storms, allowing large structures to settle gently rather than break apart through constant motion. The ship came to rest in pieces, but they landed with a quiet finality, preserved in position by stillness and sediment. Pressure added its own influence. The weight of the water compressed air-filled spaces and altered the balance of materials. Compartments collapsed inward, lighter elements flattened or cracked. Heavier sections endured, bearing the load through their shape and mass. Over time, the wreck adjusted to its surroundings, becoming part of the seafloor rather than a foreign presence upon it. Decay in these depths follows a different schedule. Cold water slows the activity of organisms that consume organic matter, while limited oxygen restricts corrosion. Steel reacts, but more slowly, forming fragile layers that flake away in thin sheets. Wood, where it remains, changes texture and density rather than disappearing outright. The process is uneven, shaped by currents, microbes, and the way sediment settles across exposed surfaces. In certain places, life has found opportunity. Microorganisms capable of surviving in cold, dark conditions colonize metal, drawing energy from chemical reactions rather than sunlight. Their activity is steady and methodical, transforming steel into rust formations that grow outward like delicate structures. This transformation takes time measured in decades, unfolding quietly without disturbance. The deep Atlantic also preserves absence. Empty corridors remain open. Stairways descend into darkness that has not shifted since the moment of arrival. Objects rest where gravity placed them, undisturbed by scavengers or currents strong enough to scatter them. The impression left behind is one of pause rather than erasure, as if motion simply stopped and the environment agreed to keep it that way. Discovery did not change these conditions. When the wreck was finally found, it appeared not as a single object but as a field of remains spread gently across the seabed. Its survival in recognizable form was a consequence of depth and cold working together, shielding it from the rapid decay that would have claimed it elsewhere. The Atlantic had kept it not through preservation alone, but through isolation. Here, decay does not rush, it proceeds with patience, guided by temperature, pressure, and chemistry rather than time at the surface. The ship continues to change, slowly yielding to its surroundings, but it does so on the ocean's schedule. In the cold dark, the Atlantic allows history to linger, suspended in a quiet balance between endurance and return. During the long years, when the Atlantic carried the weight of global conflict, the ocean absorbed a silent fleet beneath its surface. Submarines moved through the water with minimal trace, shaped to disappear even before they were lost. When many of them failed to return, they slipped into the deep with little ceremony, settling into an environment already skilled at holding what sank. These vessels were designed for concealment, and that purpose continued after they were gone. Their final positions were often unrecorded, marked only by brief signals, disrupted transmissions, or absence. In the chaos of wartime movement, exact locations blurred quickly. Storms passed, currents shifted, combat zones moved on. By the time peace returned, the Atlantic had already folded these submarines into its vastness. Recovery was never simple. Many of the losses occurred far from shore, above depths that exceeded the limits of early technology. The ocean floor in these regions was poorly mapped, its contours unknown and its conditions hostile to extended search. Even when approximate coordinates existed, the seafloor below offered countless places to hide: valleys, slopes, and sediment fields where steel could rest unseen for decades. Time added its own complications. As years passed, wrecks settled further into the seabed, becoming part of it rather than objects upon it. Sediments drifted down and accumulated slowly, softening outlines and obscuring features that sonar might once have detected more easily. In some cases, currents nudged hulls along gentle gradients, shifting them just enough to evade repeated searches. The deep Atlantic preserved these submarines in a particular way. Cold water slowed corrosion, allowing steel structures to endure longer than expected. Pressure pressed evenly from all sides, stabilizing wrecks against collapse once they had settled. Without waves or surface turbulence, the remains stayed largely where they came to rest. Many now lie intact in form, though altered in texture and strength. Their steel continues to interact with the ocean around it. Salt water works patiently, converting surfaces into layers of rust that peel and reform over time. Microorganisms adapted to the deep colonize these structures, feeding on chemical reactions that occur at the boundary between metal and water. This transformation happens gradually, turning hulls into habitats rather than debris. Each submarine resting on the ocean floor carries its own quiet history. Some sit upright, as if paused mid-journey. Others lie at angles shaped by impact and terrain. Open hatches, bent propellers, and collapsed sections speak not of drama, but of physics and pressure completing their work. The Atlantic does not arrange these remains for display. It leaves them where motion ended. Many of these sites remain undisturbed. Their depth and isolation discourage interference, allowing them to exist in a kind of suspended anonymity. They are known not through frequent observation, but through absence from the surface world. The ocean keeps them by distance and by difficulty, not by intention. Together, these submarines form a dispersed fleet that never sails, spread across the Atlantic floor, from shallow continental margins to deep abyssal plains. Their presence adds density to the seafloor's layered story, one more chapter written in steel and silence. Over time, they become less distinct as vessels and more integrated as features of the deep. The Atlantic holds this ghost fleet without emphasis. Water moves above. Currents continue their long circulation. Far below, the submarines remain, shaped slowly by chemistry and pressure. They do not drift, and they do not rise. Their steel rests where it fell, becoming part of the ocean's memory, quiet and enduring beneath the moving world above. Long after the last convoys crossed the Atlantic, the ocean continued to carry their weight. Cargo ships once moved in steady lines across these waters, heavy with supplies, fuel, food, and machinery meant to keep distant fronts alive. When many of them were lost, they did not vanish into abstraction. They descended, one by one, into the Atlantic's depths, settling across a vast corridor that stretches from continental shelves to open ocean basins. These ships were built for endurance, their hulls thick, their holds reinforced to bear immense loads. When they sank, that mass guided their descent. Steel cut through water and met the seafloor with force that reshaped both vessel and ground. Some broke apart on the way down, scattering cargo across wide areas. Others arrived more intact, their structures absorbing impact and coming to rest in long silhouettes that still echo their original form. Crews were carried with them, not as stories but as presence. In the cold, dark conditions below, movement ceased quickly. The environment allowed little disturbance, and what remained was held where it fell. Over time, sediment drifted down and gathered, softening outlines and sealing spaces. The Atlantic did not erase these ships quickly. It layered them gently into the seabed, incorporating them into its own structure. Many of these wrecks carried fuel in quantities meant to power long journeys. That fuel did not disappear when the ships went down. Encased in tanks and compartments, oil remained trapped for years, sometimes decades. Steel walls corroded slowly in the cold, saltwater environment thinning unevenly until small openings formed. Through these gaps, oil seeped out, not in bursts, but in steady, patient release. This leakage continues in places even now. Thin streams rise from wrecks and spread into surrounding sediment, darkening the seafloor and altering local chemistry. Microorganisms gather at these sites, using the oil as energy, transforming it into different compounds that drift away or settle back down. The process is slow and localized, yet persistent, a reminder that the cargo of war did not end with sinking. Above these wrecks, the ocean surface has returned to familiar patterns. Weather passes, shipping lanes shift, the water reflects sky as it always has, yet below, the past remains active in subtle ways. Rust forms, flakes away, and reforms. Oil moves gradually, tracing paths through sand and rock. The wrecks continue to interact with their surroundings, long after their purpose ended. The Atlantic remembers the war not through noise or spectacle, but through accumulation. Thousands of ships now rest along its floor, each contributing weight, material, and chemistry to the deep. Together, they form an extended graveyard, not concentrated in one place, but spread across the routes that once mattered most. The ocean holds them in silence, their presence detectable only through careful observation. This memory is not static. It changes slowly as materials degrade and environments adjust. Steel weakens, cargo disperses, life adapts to what was introduced. The war's imprint becomes less distinct with each passing decade, yet it does not vanish. It blends into the Atlantic's layered history, becoming another stratum among many. In this way, the ocean carries human conflict forward without emphasis. It does not retell events or preserve intention. It simply keeps what entered it, allowing the consequences to unfold at their own pace. The Atlantic still remembers the war because its depths are patient and because nothing that sinks into them is ever entirely gone. In earlier centuries, the Atlantic carried vessels whose purpose was expansion rather than speed. Wooden hulls crossed unfamiliar water loaded with gold, silver, spices, people, and promise. These ships traveled routes that were still being imagined, guided by stars, incomplete charts, and confidence borrowed from experience rather than certainty. Many never completed their passages, and the ocean accepted them without witness. Gold fleets moved in seasonal rhythms, leaving ports heavy with wealth gathered from distant lands. Their holds strained under coins, ingots, and artifacts meant to reshape economies far away. These ships followed narrow windows of favorable weather, yet timing was imperfect and conditions unpredictable. Storms rose quickly along their paths. Currents pushed against progress. When fleets were scattered, some ships did not regroup. Their disappearance left gaps in ledgers that could not be filled with explanation. Slave ships crossed the Atlantic under very different conditions, carrying human lives forced into the darkest form of commerce. These vessels were often overcrowded, poorly maintained, and pushed to their limits by urgency and profit. Disease spread quickly. Structural failures went unrepaired. When storms or navigation errors struck, there was little margin for survival. Many such ships vanished without record, their loss unnoted beyond the absence of an expected arrival. Exploration vessels faced another set of uncertainties. Charged with mapping coastlines and searching for passages, they ventured into waters where depth, weather, and coastline were poorly understood. These ships traveled without the benefit of reliable longitude, making their positions difficult to track even when conditions were calm. A single miscalculation could carry them into unfamiliar currents or hidden shoals. When they failed to return, there were often no witnesses to offer clarity. Records from this era were fragile. Logs were written by hand and stored aboard the vessels themselves. When a ship was lost, its documentation usually vanished with it. News traveled slowly, filtered through rumor and delayed reports. A missing ship might be assumed late rather than lost, its fate unresolved for years. By the time concern hardened into certainty, the ocean had already erased surface traces. Political and economic pressures also shaped what was remembered. Not every loss was recorded with care. Some disappearances were quietly accepted to avoid financial consequence or scrutiny. Others occurred along routes considered routine, where danger was underestimated and oversight minimal. The absence of records does not always reflect mystery, but the limits of attention and accountability at the time. The Atlantic floor holds what the written record does not. Beneath layers of sediment rest ships that carried wealth and suffering in equal measure, their remains scattered along routes that once defined empires. Some lie broken apart, cargo dispersed by impact and time. Others remain more intact, their shapes preserved by depth and cold, unmarked by the world that moved on above them. These wrecks rarely announce themselves. They are found slowly through chance discoveries or careful survey, emerging from darkness without names attached. Without documentation, identification becomes uncertain. A hull fragment might belong to a merchant ship or an exploration vessel. Cargo may suggest intent, but certainty remains elusive. The Atlantic absorbed these ships during a period when crossing it required belief as much as preparation. It offered opportunity and risk in equal measure, and it did not guarantee return. Many voyages ended beyond sight of land and beyond the reach of record keepers. What remains is a scattered inheritance of loss, resting quietly beneath modern roots, carried forward by an ocean that keeps its earliest crossings without explanation or display. Beneath the Atlantic's rolling surface rises a landscape that mirrors the drama of continents, yet remains concealed by water and distance. Mountains climb from the seafloor in long ridges and solitary peaks, their summits sometimes stopping far below the reach of light. These formations did not grow upward toward air. They accumulated patiently, built from eruptions and uplift that never breached the surface, leaving their presence to be felt rather than seen. Seamounts form where magma escapes through weaknesses in the crust, spreading outward and hardening layer by layer. Over immense spans of time, these deposits pile into steep structures, some rising thousands of meters from the surrounding seabed. Underwater volcanoes follow similar paths, occasionally active, often dormant, shaped by cycles of eruption and quiet cooling. Together, they create a rugged terrain hidden beneath what appears from above to be open ocean. For ships, this hidden relief has long posed danger. Early navigators assumed deep water offered safety, believing hazards lay close to shore. In regions scattered with seamounts, that assumption failed. A vessel could cross calm seas, its keel clearing ordinary depths, while an unseen mountain rose sharply beneath it. Without warning, hulls met stone, tearing open on slopes no chart had recorded. Even today, the risk remains in subtle form. While modern ships are better equipped, not all underwater mountains are tall enough to breach common depth alarms. Some rise just short of the surface, altering currents and creating localized turbulence rather than direct impact. These disruptions can strain hulls and affect control, especially in poor visibility or heavy weather. The danger is not always collision, but the indirect force of water pushed upward and sideways by rock below. Mapping these features has always been difficult. The Atlantic is vast, and much of its floor remains far beyond direct observation. Early charts relied on soundings taken sporadically, measuring depth at single points and leaving vast spaces between them unmeasured. A seamount could easily sit unnoticed between readings, its presence inferred only after a ship failed to arrive. Even with advanced technology, coverage remains incomplete. Detailed sonar mapping is slow and resource-intensive, requiring vessels to pass methodically back and forth across areas that span thousands of kilometers. Many regions have been surveyed only at low resolution, revealing broad trends while missing smaller, sharper features. Seamounts with narrow peaks can escape detection until encountered directly or revealed through later analysis. Underwater volcanoes add further complexity. Their shapes can change over time as eruptions deposit new material or collapse existing structures. A previously charted rise may grow taller or shift its profile without any sign at the surface. In these cases, maps represent a moment in time rather than a fixed truth, requiring continual revision that the scale of the ocean rarely allows. These hidden mountains also influence the Atlantic's movement. Currents encountering steep relief are diverted upward, creating zones of mixing and turbulence that affect water temperature and nutrient flow. Life gathers around these areas, drawn by increased productivity, yet the same forces that sustain ecosystems can challenge navigation. What nourishes the deep also complicates passage. The Atlantic holds thousands of these submerged peaks, scattered unevenly across its basin. Many are known only through indirect signs, such as changes in current behavior or unexplained depth variations. Others remain entirely undocumented, rising silently from the floor with no name or record. In this concealed terrain, the ocean reveals a quiet defiance of complete knowledge. Water smooths the surface, hiding what lies beneath. Ships pass above unaware, their routes drawn across a landscape still being discovered. The Atlantic's mountains endure in shadow, shaping movement and memory while remaining just beyond reach of certainty. In the deep Atlantic, sound travels farther than sight ever could. Light fades quickly, but vibrations move through water with ease, bending around terrain and carrying information across great distances. In this darkness, the ocean has been listening to itself for far longer than humans have been listening in return. When instruments were finally placed into these depths, they began to register sounds that did not belong to waves, storms, or passing ships. Some of these recordings are low and prolonged, stretching across frequencies below human hearing. They rise slowly, linger, and fade, sometimes lasting minutes, sometimes returning in repeating patterns. Others appear as brief pulses, sharp enough to stand out against the steady background of the sea. These sounds are not loud in the way surface noise is loud. They are heavy, resonant, and difficult to localize, as if the water itself is speaking. Scientists studying these signals look first to the moving Earth. The Atlantic floor is active, shaped by spreading crust, shifting faults, and the slow release of pressure built over time. When rock bends or slips, it can release energy as sound, sending vibrations into the surrounding water. Even small movements, imperceptible at the surface, may echo across vast distances below. In some cases, these sounds align with known seismic events, offering a natural explanation grounded in geology. Ice also contributes its voice. In colder regions, large masses of ice crack, fracture, and drift. When this happens underwater, the sound can travel far from its source, reshaped by depth and temperature into something unfamiliar. What begins as a simple fracture can arrive at a listening instrument as a drawn-out moan or rising tone, altered by the path it traveled. Biology plays a role as well. Large marine animals communicate using low frequencies designed to move efficiently through water. Their calls can be powerful enough to register thousands of kilometers away. In areas where life gathers near seamounts or deep ridges, these biological signals layer atop geological noise, blending movement and intention into a complex acoustic landscape. Yet, not every sound fits neatly into known categories. Some recordings resist clear explanation, even after careful comparison with seismic data, ice movement, and biological activity. These signals may appear in isolation, without accompanying events or consistent repetition. They emerge briefly, then do not return, leaving little opportunity for direct study. Part of the challenge lies in the nature of the ocean itself. Sound changes as it moves, reflecting off slopes, bending with temperature layers, and stretching across time as it travels. By the moment a signal is recorded, it has already been shaped by distance and environment. Locating its origin becomes difficult, especially in regions where terrain drops sharply and currents shift unpredictably. Instrumentation also has limits. Hydrophones listen passively, capturing whatever passes through their range without context. A single recording station offers only part of a wider picture. Without multiple reference points, interpreting direction and source remains uncertain. Many sounds may be common occurrences heard rarely, while others may be genuinely infrequent. What remains unexplained does not suggest absence of cause, but complexity of system. The Atlantic is a layered environment where geology, biology, and physics overlap constantly. Some sounds may arise from interactions rather than single sources, moments when multiple processes align briefly to produce something distinct. Over time, patterns slowly emerge. As listening continues, certain sounds repeat under similar conditions, allowing tentative connections to be drawn. Others fade into the background, becoming part of the ocean's constant murmur. A few persist as anomalies, quiet reminders that understanding lags behind observation. In the deep, the Atlantic speaks in vibrations shaped by pressure, movement, and life. Most of what it says can be translated with patience and data. Some messages remain untranslated, not because they are hidden, but because the ocean's language is layered, ancient, and still being learned. As depth increases in the Atlantic, pressure becomes the defining force. It arrives gradually at first, felt only as a steady tightening, but it grows relentless with every meter of descent. Water bears weight without rest, and that weight presses inward from all sides at once. In the deep, there is no direction without pressure. Above, below, and around, it is the same unyielding presence. Submarines are built to endure this environment through careful balance. Their hulls are shaped to distribute force evenly, curved to prevent stress from collecting at corners or seams. Materials are chosen not just for strength, but for predictability under compression. Even so, the margin for error is narrow. Each vessel is designed for a specific depth range, beyond which the surrounding water no longer allows compromise. When a submarine descends past its intended limits, the structure begins to respond in subtle ways. Metal flexes inward by tiny degrees. Seals compress. Components designed to remain round or rigid begin to deform. These changes may not be immediately visible, but they alter how force moves through the hull. Pressure searches for weakness, not through violence, but through persistence. If a critical point is reached, failure comes without transition. An implosion is not an explosion reversed. It is the sudden surrender of structure to an external force that has been present all along. Once a hull gives way, even by a small fracture, water rushes inward faster than any material can react. The collapse propagates instantly, folding steel inward with decisive finality. The speed of this event is shaped by physics rather than circumstance. Water at depth carries immense energy due to its density and compression. When allowed entry, it releases that energy in a single, overwhelming movement. Compartments vanish. Air is eliminated in fractions of a second. The transformation from sealed vessel to debris occurs before sound has time to travel outward. This immediacy leaves no space for intervention. Rescue depends on time, communication, and access, all of which are absent at extreme depth. Signals weaken as they pass through water and pressure-resistant structures. Even when a location is known, reaching it requires equipment capable of withstanding the same forces that caused the failure. The ocean does not pause to allow response. Depth also imposes distance. Submersible vehicles move slowly, constrained by careful control and limited power. Each descent is deliberate, measured, and narrow in scope. Vast areas of the Atlantic remain beyond practical reach, their depths mapped only in outline. In such conditions, recovery is not a matter of willingness, but of physical possibility. The environment itself complicates every attempt. Cold thickens hydraulic fluids and stiffens materials. Currents near the bottom follow complex paths shaped by unseen terrain. Visibility is minimal, and orientation relies entirely on instruments that must function under pressure without fault. Any rescue effort becomes an exercise in precision within margins that allow no deviation. What remains after an implosion settles quietly. Fragments descend and come to rest among sediment and slope. Pressure equalizes, and movement ceases. The ocean absorbs the event without acknowledgement, continuing its circulation above and around the site. There is no surface disturbance, no lasting signal, only a silent adjustment beneath. In the deep Atlantic, pressure governs outcome with calm certainty. It does not rush or threaten. It exists as a constant condition that rewards preparation and exactness and reacts instantly when limits are crossed. Steel, no matter how carefully shaped, must yield when those limits are exceeded. This reality defines the boundary between exploration and loss. It explains why descent must be cautious, why structures are conservative, and why rescue remains constrained. In these depths, the Atlantic does not act against intruders. It simply remains itself, dense, heavy, and precise, allowing only what can endure its weight to remain intact. At the deepest levels of the Atlantic, temperature becomes architecture. Water does not simply circulate here, it settles, layers itself, and remains. In the coldest regions near the poles, surface water cools until it grows heavier than the layers beneath it. Salt increases its density further, and gravity does the rest. The water begins a slow descent, sinking away from light and weather into the interior of the ocean. This sinking does not happen in a rush. It unfolds as a broad, quiet movement, spreading outward from its source like a deep breath released beneath the surface. Once below, the cold water travels along the contours of the seafloor, guided by pressure and shape rather than wind. It slips into basins, fills trenches, and settles into the lowest places the Atlantic has carved over time. Because cold water is dense, it resists rising again. Warmer layers float above it, forming a stable arrangement that can persist for centuries. In this structure, the deepest regions remain filled with water that has not seen the surface since long before modern observation. The Atlantic's cold bottom water becomes a foundation, supporting everything above it while rarely being disturbed itself. This slow filling of depth explains why the coldest water reaches the lowest places first. Trenches, basins, and deep plains act as reservoirs, collecting and holding this dense layer. Once established, it spreads laterally, flowing across the abyss in measured paths that ignore surface boundaries. The deepest Atlantic becomes unified by this shared cold, linking distant regions through temperature rather than geography. The presence of this bottom water shapes the chemistry of the deep. Cold holds more dissolved gases, including oxygen carried downward from polar regions. This supply sustains life in places far removed from surface exchange. Nutrients travel with the flow as well, redistributed slowly across the ocean floor. The deep Atlantic becomes not stagnant, but quietly nourished by movement that happens too slowly to notice without instruments. Life adapts precisely to these conditions. Organisms here are shaped by constant cold, immense pressure, and limited energy. Metabolism slows, growth becomes deliberate. Bodies are built to conserve rather than expend. Many species rely on the steady delivery of organic material drifting down from above, while others draw energy from chemical processes tied to the seafloor itself. The cold bottom water provides consistency, allowing life to persist without fluctuation. This water also controls how sound travels, how currents bend, and how sediment settles. Its temperature and density influence the behavior of layers above it, shaping circulation patterns throughout the Atlantic. In this way, the cold at the bottom exerts influence far beyond its immediate surroundings, anchoring the ocean's internal structure. When disturbances occur above, storms, shifting currents, passing waves, the deepest water remains largely unchanged. It absorbs pressure without motion, responding slowly, if at all. This stability gives the deep Atlantic its distinct character, a sense of permanence beneath constant surface change. Time moves differently here, marked not by days or seasons, but by gradual shifts in chemistry and flow. The cold bottom water does not seek attention. It spreads, fills, and remains, quietly defining the limits of the ocean's interior. By sinking and staying, it creates the conditions that allow the deep Atlantic to function as a connected system rather than a collection of isolated depths. In this layered stillness, life continues, pressure persists, and the ocean holds its cold foundation intact. The Atlantic rests upon this hidden cold, its deepest places shaped and sustained by water that sinks, spreads, and patiently governs the world beneath the surface. Below the Atlantic's last traces of light, life settles into a permanent night. Here, depth is not an absence but a condition that shapes every movement, every form, and every exchange of energy. Fish and invertebrates exist in a world defined by pressure so constant it feels like part of the body itself, pressing evenly from all sides, leaving no space for emptiness. Fish adapted to these depths are shaped differently from those above. Bones are lighter, sometimes reduced, allowing bodies to withstand compression without cracking. Muscles are soft and elastic, built for efficiency rather than speed. Many lack rigid swim bladders, relying instead on oils or flexible tissues that do not collapse under pressure. Movement is slow and deliberate, conserving energy in a place where food arrives unpredictably and in small amounts. Eyes, when present, tell their own story. Some species carry enormous eyes, tuned to capture the faintest glimmers of passing bioluminescence. Others abandon vision almost entirely, their senses redirected toward vibration, chemical traces, or subtle changes in water movement. In eternal night, awareness replaces sight, and perception stretches outward through senses unfamiliar to surface life. Light does exist here, but it is made rather than received. Glowing organisms illuminate themselves through chemical reactions within their bodies, producing soft blues and greens that travel far in darkness. This bioluminescence serves many roles. Some creatures use it to lure prey closer, presenting gentle signals that draw attention in an otherwise empty field. Others flash briefly to confuse or distract, breaking outlines and buying moments of escape. There are those who glow to communicate. Patterns of light pulse in slow rhythms, signaling presence, readiness, or boundary. In a world without landmarks, light becomes language. It replaces color, movement, and sound, carrying meaning across meters of black water. These signals are precise, refined by generations shaped entirely by darkness. The Atlantic's deep life appears strange because it follows rules unfamiliar to surface ecosystems. There is no reliance on sunlight, no daily cycle to guide behavior. Instead, time is measured by scarcity and patience. Feeding may occur infrequently, when organic material drifts down from above or when a rare encounter presents itself. As a result, bodies are built to endure long intervals without nourishment. Many deep-sea creatures grow slowly and live longer than their shallow water relatives. Their metabolism reflects the stability of their environment, where temperature barely changes and seasons do not exist. Growth is an investment made cautiously, aligned with an environment that rewards persistence over speed. In this stillness, survival depends on avoiding waste rather than maximizing output. Pressure also shapes appearance. Limbs may be elongated or reduced. Skins are thin. sometimes transparent, allowing internal organs to be visible. This is not vulnerability, but efficiency. Pigmentation becomes unnecessary where light does not penetrate. Structure adapts to physics rather than display. The Atlantic's depths are not empty, but sparsely populated. Life is spread thinly, with large distances between encounters. This spacing reduces competition and lowers the chance of detection. It creates a quiet community bound not by interaction, but by shared conditions. Each organism occupies its own small domain within a vast, dark volume of water. What emerges from this environment feels unfamiliar because it reflects an ancient adaptation to extremes. The deep Atlantic has existed in darkness for millions of years, allowing evolution to explore forms unconstrained by light or warmth. The result is life that feels otherworldly, not because it is exotic, but because it is perfectly matched to conditions far removed from the surface. In eternal night, the Atlantic carries a living archive of pressure, patience, and chemical light. These creatures drift, glow, and endure in silence, shaped by depth into forms that seem strange only when viewed from above. Along the Atlantic's deepest fractures, warmth escapes quietly from the Earth itself. Far below the reach of sunlight, seawater seeps down through cracks in the crust, traveling toward rock still heated by the planet's interior. There, it warms, absorbs minerals, and rises again, returning to the ocean transformed. These slow circulations give rise to hydrothermal vents, places where the seafloor breathes heat into a cold, pressurized world. The water that emerges is unlike the surrounding sea. It is enriched with dissolved metals and chemicals drawn from deep rock, carrying iron, sulfur, and other elements in invisible suspension. When it meets the frigid Atlantic depths, these minerals precipitate, forming billowing clouds that darken the water like smoke. Over time, this process builds towering chimneys of mineral deposits, structures that grow gradually, layer by layer, shaped by chemistry rather than erosion. Around these vents, temperature changes abruptly. The surrounding water remains near freezing, while vent fluid can be dramatically warmer just meters away. This contrast creates steep gradients that define narrow zones of habitability. Life does not spread evenly here. It gathers closely, clustering around the warmth and chemistry that sustain it. Unlike surface ecosystems, vent communities rely on no sunlight at all. Energy arrives not from photosynthesis, but from chemical reactions. Microorganisms use compounds in the vent water to fuel their metabolism, converting chemicals into usable energy through processes adapted to darkness and heat. These microbes form the foundation of an ecosystem that exists entirely independent of the sun. Larger organisms build upon this base. Worms, crustaceans, and other invertebrates host or graze upon these microbes, forming partnerships that allow survival in conditions once thought uninhabitable. Some species lack mouths or digestive systems entirely, relying instead on internal bacteria to process chemicals directly. Bodies grow in shapes and textures unfamiliar to surface life, reflecting adaptation to pressure, warmth, and scarcity. The Atlantic's hydrothermal vents feel otherworldly because they defy expectations built from surface experience. Here, warmth rises from below rather than falling from above. Darkness is constant, yet life flourishes. Structures grow without soil, leaves, or light, assembled instead from mineral precipitation and biological persistence. Motion is slow and deliberate, shaped by a stable environment that changes little over time. Sound behaves differently near these sites, softened by rising fluids and uneven terrain. Visibility is limited, not only by darkness, but by clouds of mineral-rich water drifting outward from vent openings. Instruments register sharp contrasts over short distances, heat beside cold, chemistry beside emptiness. The environment feels compartmentalized, as if the ocean has folded itself into small, intense pockets of activity. These vents also remind us that the Atlantic is connected to processes far deeper than its water alone. Heat from the planet's interior participates directly in shaping ecosystems, linking geology and biology in continuous exchange. The seafloor is not merely a boundary, but an active interface where rock, water, and life interact. Over time, vents can change or fade, chimneys collapse, pathways clog, new openings appear nearby as water finds alternate routes through the crust. Life adjusts accordingly, migrating short distances to follow suitable conditions. The ecosystem persists not through permanence, but through flexibility within a narrow range of tolerable extremes. In the surrounding deep, where cold bottom water dominates, these vent fields stand out as islands of warmth and motion. They punctuate the Atlantic's darkness with localized vitality, places where the planet quietly shares its internal energy with the ocean above. Hydrothermal vents reveal a version of life shaped by forces beyond light and weather. They show that the Atlantic's depths are not uniform, but textured with hidden environments that feel distant from the surface world. In these warm fractures, the ocean carries proof that life can arise wherever energy flows, even in darkness that never lifts. Once a ship reaches the Atlantic floor, its journey is not always finished. Beneath the calm suggested by depth, the seabed is rarely still. Water continues to move there, slower than at the surface, but persistent enough to shape what rests upon it. These deep currents do not rush. They press, slide, and circulate with quiet determination, applying force not through speed, but through time. As water travels along the contours of the ocean floor, it follows slopes and channels carved by geology and sediment. Where the ground tilts, even slightly, gravity assists the flow, guiding currents downslope and around obstacles. A wreck resting in this environment becomes part of that landscape. Its structure interrupts the flow, creating zones of pressure on one side and reduced resistance on the other. Over years, this imbalance can begin to matter. Sediment plays an important role. Fine particles carried by deep currents settle continuously, building thin layers that can alternately support or destabilize a wreck. When sediment accumulates unevenly, one section may become anchored while another remains exposed. Currents passing over exposed areas apply gradual force, nudging hulls or rotating sections by small degrees. These movements are too slow to notice directly, yet they accumulate over decades. In some regions, the seabed itself moves. Slopes composed of loosely packed material can creep downslope under their own weight, a process so gradual it appears motionless. Any object resting on such ground moves with it, carried along as the sediment migrates. A wreck may descend only meters over many years, but those meters add up, relocating it far from the point where it first arrived. Currents also vary with depth. Layers of water move in different directions, shaped by temperature, density, and the structure of the basin. A wreck descending through these layers may be pushed laterally as it falls, landing offset from its sinking position. Lighter debris separates and follows its own paths, spreading across the seabed in patterns that do not point back to the original event. When such sites are eventually discovered, their positions can appear puzzling. The wreck lies far from expected shipping lanes or recorded coordinates. Surrounding debris fields may be elongated or fragmented, offering no clear center. Without understanding the slow choreography of currents and sediment, the location seems to contradict logic. This is why maps of wreck sites often carry uncertainty. Coordinates reflect moments of observation rather than fixed truths. A ship documented at one position may shift slightly before the next survey, or may have moved long before it was ever found. Early records relied on surface reports that did not account for subsurface drift. Even modern mapping represents snapshots in a system that continues to change. The Atlantic amplifies this uncertainty through scale. The ocean floor is immense, and even detailed surveys cover limited areas. Between mapped zones lie stretches where depth, slope, and current behavior remain inferred rather than measured. A wreck moving slowly through such regions leaves little trace of its path, making reconstruction difficult. Technology improves precision, but it cannot freeze motion. Sonar images show form and position at the time of scanning, not history. Sediment layers reveal some movement, but interpretation requires context that is not always available. As a result, maps become living documents, updated and corrected as new data emerges. These moving wrecks remind us that the deep ocean operates on timelines unfamiliar to surface life. Change happens without urgency, but without pause. The Atlantic does not keep objects where they first arrive. It carries them gently, reshapes their surroundings, and adjusts their position in ways that challenge assumptions of permanence. What sank in one place may rest in another, not through violence, but through patient movement. Currents slide past, sediment shifts, the seabed inclines. Over time, the wreck becomes less a marker of a single event and more a participant in the ocean's ongoing rearrangement. In this way, the Atlantic continues to move what it has taken, quietly reminding us that even in stillness, the deep is never truly fixed. In the North Atlantic, cold arrives with patience and scale. Along high latitudes, winter tightens its grip on water and coastline alike, allowing ice to form where fresh water meets the sea and where glaciers release their weight into open water. These fragments do not announce themselves as threats. They separate quietly from ice shelves and coastal glaciers, slipping into the ocean with little disturbance, shaped by fractures that began long before they reached the surface. Once afloat, icebergs become travelers. Their visible forms suggest modest size, yet most of their mass lies hidden below the waterline, extending deep into the cold Atlantic. This imbalance gives them stability and persistence. They drift not as passive objects, but as participants in the ocean's layered motion, guided by currents that move steadily southward from polar regions. Cold currents carry these icebergs into temperate waters where shipping routes converge. The same circulation that moderates climates also delivers ice far from its origin. As the water warms, the ice does not vanish immediately. It melts slowly, preserving its structure long enough to cross paths with vessels that assume danger has passed with latitude. Icebergs do not follow straight lines. Their movement reflects a balance between surface winds pushing exposed ice and deeper currents steering the submerged mass. Changes in weather can shift their course subtly, altering direction without clear sign. Fog often accompanies these conditions, reducing visibility at the very moment when awareness matters most. The danger they pose is quiet and mechanical. Ice does not strike with force born of motion alone, it resists. When steel meets ice, the ice yields little at first, allowing pressure to concentrate along narrow points of contact. Hulls designed to cut through water encounter resistance they were never meant to meet. Damage unfolds quickly, not through noise or spectacle, but through breach and flooding. Modern technology has reduced uncertainty, but it has not removed it. Satellite tracking identifies large icebergs, yet smaller fragments are harder to detect. Pieces broken from larger bodies can remain submerged just below the surface, invisible to radar and difficult to spot visually. These fragments drift independently, carried by currents that do not align with expected paths. Shipping lanes through the North Atlantic remain busy due to geography and efficiency. Routes shorten travel time and reduce fuel use, encouraging continued passage through regions where ice still appears seasonally. Mariners rely on forecasts and monitoring, yet decisions are made within moving environments. Conditions change between updates. Ice shifts between reports. Collisions continue because the system allows little margin for error. Large ships cannot stop quickly. Course changes require space and time. When visibility is reduced, reaction windows narrow further. Even awareness does not guarantee avoidance when mass and momentum are involved. The Atlantic does not preserve ice indefinitely. As icebergs move into warmer water, they thin and weaken, releasing cold fresh water into the surrounding sea. This melt alters local conditions, sometimes increasing fog or changing current behavior. The final dissolution occurs gradually, without signal, leaving behind only water indistinguishable from the rest. This cycle repeats each year with variation rather than predictability. Some seasons produce more ice, others send fragments farther than expected. The process remains shaped by climate, currents, and chance alignment. For those crossing the North Atlantic, ice remains a presence rather than a memory. Icebergs persist as silent hazards because they belong to the ocean's natural rhythm. They form, drift, and disappear without intention. In doing so, they remind ships and routes alike that even well-traveled waters carry elements that resist control. The Atlantic accepts ice into its flow and carries it onward, allowing danger to arrive quietly, carried by cold and time. The Atlantic has a reputation for changing its mood without warning. One moment, the surface can lie smooth and reflective, carrying ships across long distances with little resistance. The next, the same water rearranges itself into motion that feels sudden and unmistakable. This transformation does not arrive as a single event, but as a rapid layering of forces that were already present, waiting to align. Calm seas can turn violent when temperature differences meet moving air. Warm water releases energy steadily into the atmosphere, and cooler air passing above it becomes unstable. This instability may not announce itself far in advance. Subtle shifts in wind direction or pressure allow rising air to organize quickly, gathering strength as it pulls more energy from the ocean below. The surface responds, losing its smoothness as wind transfers momentum into waves that grow taller and closer together. The Atlantic's geography adds to this effect. Warm and cold currents meet across its surface, creating sharp boundaries where air masses clash. Along these invisible lines, weather can intensify rapidly. Clouds thicken, winds accelerate, waves steepen as water moving in different directions collides. What began as moderate motion can escalate within hours, reshaping conditions before adjustment is possible. Forecasting these changes remains a challenge because the system is layered and dynamic. Weather models rely on vast amounts of data, yet they work by approximation rather than certainty. Small variations in temperature or wind can amplify quickly in the Atlantic, producing outcomes that diverge from prediction. The ocean's surface may appear stable in satellite imagery, while the atmosphere above organizes faster than expected. Timing plays a critical role. Many Atlantic storms form locally, drawing strength from the water beneath them rather than arriving fully developed from distant regions. This local development reduces advance notice. Instruments capture snapshots of evolving conditions, but rapid intensification can occur between updates. By the time changes are fully recognized, they are already unfolding. The ocean itself influences these limits. Heat stored in deeper layers can resurface through mixing, feeding storms that models assumed would weaken. Currents alter wave patterns, allowing energy to stack into chaotic seas. These interactions happen continuously, making the Atlantic a place where prediction must contend with constant motion rather than stable background conditions. For sailors, this unpredictability has shaped experience and memory. Generations have learned that the Atlantic does not require extreme distance or rare alignment to become dangerous. Familiar routes have carried unexpected storms. Calm horizons have preceded heavy seas. Accounts passed between mariners emphasize respect rather than confidence, a recognition that conditions here reward caution and patience. Fear does not arise from spectacle alone, but from inconsistency. In oceans where patterns repeat predictably, preparation offers reassurance. In the Atlantic, preparation coexists with uncertainty. Crews may do everything correctly and still encounter conditions that exceed expectation. This awareness settles quietly into maritime culture, shaping how passages are planned and remembered. The surface calm can be misleading because energy remains stored beneath it. Wind may be light while currents move strongly below. Pressure gradients may tighten without immediate visual signal. The Atlantic holds these contrasts together, allowing transformation to occur swiftly when balances shift. When weather subsides, it does so with equal subtlety. Waves stretch and flatten, winds soften. The ocean returns to an appearance of ease, leaving behind little trace of intensity. This return reinforces the impression that violence emerged unexpectedly, even though it was the product of gradual alignment rather than sudden creation. The Atlantic's sudden weather reflects the nature of a system always in exchange. Heat, air, and water interact constantly, sometimes gently, sometimes decisively. Sailors fear this ocean not because it is always rough, but because it is never entirely settled. Beneath moments of calm lies the potential for rapid change, carried quietly until conditions allow it to rise. Over the Atlantic, navigation depends on reference and trust. When that trust falters, motion continues without certainty. Lost Flight 19 unfolded within this fragile space, not as a sudden disappearance, but as a gradual separation from reliable orientation. The aircraft did not vanish in an instant. They flew on, minute after minute, moving through air that offered few stable markers once familiar bearings failed. The region where this occurred carries subtle complications for navigation. Magnetic variation shifts gently across the Atlantic, changing angle and intensity depending on position and altitude. For pilots trained to rely on compasses as steady guides, even small deviations can accumulate. When readings disagree with expected headings, confidence begins to erode. Corrections made to fix one perceived error may introduce another. As Flight 19 progressed, communication reflected this growing uncertainty. Pilots reported confusion rather than alarm, indicating a process unfolding rather than a crisis erupting. Headings that should have returned them to land instead carried them farther out. Each adjustment compounded distance, stretching the search area wider with every passing moment. Over open water, there were no landmarks to contradict faulty instruments. Compasses can fail without breaking. Magnetic interference, instrument calibration, and environmental factors all influence their behavior. In regions where magnetic lines bend irregularly, readings may drift or fluctuate subtly. When multiple instruments are affected similarly, cross-checking becomes less useful. The result is not chaos, but convergence on a shared error. Weather layered itself into this situation. Conditions above the Atlantic can change quickly, cloud cover reducing visibility and obscuring the horizon. Without visual reference, reliance on instruments increases. Wind also exerts quiet influence, pushing aircraft off course gradually. These forces do not announce themselves sharply. They work slowly, aligning with misread instruments to guide flight paths away from expectation. Fuel limits imposed a boundary that could not be negotiated. Aircraft continue forward until available energy is exhausted, regardless of certainty. Over water, this leads not to forced landings, but to descents without ground beneath. The Atlantic below offers no markers, only depth and motion. Once contact is lost, recovery becomes governed by probability rather than location. Search efforts face the scale of the ocean. Even with rapid response, the Atlantic presents an environment where debris disperses quickly. Currents spread material outward. Weather alters surface conditions. Without a precise endpoint, searches expand across vast areas, reducing the chance of detection. Absence becomes the only consistent signal. Scientific interpretation of the event draws from these overlapping factors rather than singular explanation. Navigation error, shaped by magnetic variation, compounded by weather and limited reference, offers a framework consistent with recorded transmissions. Aircraft behavior reflected attempt rather than panic, indicating functioning systems operating within flawed guidance. The Atlantic did not act as an active agent in this loss. It provided conditions where small errors mattered. It offered space wide enough for uncertainty to grow without correction. Once the planes descended, the ocean accepted them as it does all things that fall into it, dispersing traces according to its own movement. Lost Flight 19 remains a study in how technology and environment interact under pressure. It illustrates how disappearance can emerge from alignment rather than anomaly. No single failure defines the outcome. Instead, layers of minor deviation gathered until return was no longer possible. In this way, the Atlantic's role is quiet and consistent. It does not conceal deliberately. It simply provides scale, motion, and complexity enough that precision becomes essential. When navigation falters within this space, distance expands gently but decisively. The ocean continues its circulation above and below, holding what enters it without emphasis, leaving interpretation to those who study patterns long after signals fade. The Atlantic seafloor exists mostly beyond direct sight. While coastlines and surface routes feel familiar, the vast majority of what lies beneath remains known only through indirect signals. Mapping the ocean floor is not a matter of simple observation, but of inference, built from echoes, measurements, and models layered over time. Even now, large portions of the Atlantic remain sketched rather than fully seen. Depth is the first obstacle. Sound-based mapping systems send signals downward and measure their return, translating time into distance. This process works best in shallow regions where signals travel quickly and detail remains sharp. In the deep Atlantic, signals must cross miles of water, spreading and weakening before they return. Resolution softens with depth, turning sharp features into gentle approximations. Scale adds another challenge. The Atlantic spans immense areas, and detailed mapping requires slow, methodical coverage. Ships equipped with high-resolution sonar move deliberately, surveying narrow swaths at a time. Covering even a small fraction of the basin in fine detail can take years. As a result, mapping effort concentrates on regions of particular interest, leaving wide areas represented by coarse data. Much of what is currently known comes from satellite measurements of sea surface height. Subtle variations in gravity caused by underwater mountains and trenches slightly alter the surface above them. Satellites detect these changes, allowing scientists to infer the shape of the seafloor indirectly. This method reveals broad structures, but it cannot resolve smaller features. Seamounts, ridges, and steep slopes may remain invisible until directly surveyed. Environmental conditions also limit exploration. Weather, currents, and remoteness restrict where research vessels can operate efficiently. Some regions of the Atlantic lie far from ports, making extended surveys costly and complex. Others coincide with rough surface conditions that interfere with precise measurements. The ocean does not offer stable working ground, and mapping must adapt to its movement. As a result, gaps persist. Entire stretches of the abyssal plain remain mapped only at low resolution. Trenches may be outlined, but not detailed. Volcanic fields may appear as subtle anomalies rather than defined structures. These unknowns are not empty spaces, but areas where certainty fades into probability. Within these gaps, depth itself becomes abstract. Numbers describe distance, but form remains vague. A valley may exist where charts show a slope. A ridge may rise unnoticed beneath layers of approximation. The Atlantic holds these features quietly, its floor shaped by processes that continue regardless of documentation. Explorers look to these unknowns with measured curiosity. The goal is not conquest, but understanding. Improved mapping helps explain how currents move, how ecosystems are structured, and how geological forces interact with water above. It informs navigation, cable placement, and climate models. Each refinement clarifies relationships that extend far beyond the seafloor itself. There is also the possibility of discovery. New seamounts, previously unrecorded vent systems, and unfamiliar biological communities may wait within unmapped regions. These findings do not overturn what is known, but they add texture, revealing complexity where uniformity was assumed. Discovery here is incremental rather than dramatic, built from patience and precision. Technological advances continue to narrow the gaps. Autonomous underwater vehicles travel closer to the seabed, collecting detailed images and measurements without constant human control. Data processing improves, turning echoes into clearer representations. Yet even with these tools, complete mapping remains a distant horizon. The Atlantic seafloor resists full capture because it is vast, deep, and active. It continues to shift slowly, reshaping itself beneath layers of water. Maps improve, but they age. What remains unknown is not an oversight, but a reflection of scale. In this quiet incompleteness, the Atlantic preserves a sense of distance from the surface world. Its unseen floor reminds us that exploration is ongoing and that understanding grows gradually, guided by curiosity rather than urgency. The unknown persists, not as a mystery demanding resolution, but as a space inviting careful attention over time. Beneath the Atlantic's surface, modern traces settle quietly alongside older remains. Pollution does not arrive dramatically. It accumulates through repetition, fragment by fragment, carried by systems designed to move water rather than discard it. Plastics released at the surface rarely stay there. Sunlight weakens them, waves fracture them, and time reduces them into pieces small enough to slip into the ocean's interior. As plastics break down, their density changes. Some fragments absorb salts and organic material, becoming heavy enough to sink. Others attach to living organisms or microscopic particles that drift downward as part of the ocean's constant snowfall of matter. This slow descent carries plastic away from sight, transporting it into deeper layers where movement is steadier and removal unlikely. The Atlantic is especially effective at trapping debris because of how its currents circulate. Large surface currents converge and rotate, drawing floating material inward. What gathers at the surface eventually feeds into subsurface flows that pull fragments down and inward. Rather than dispersing evenly across the globe, debris becomes concentrated within certain regions, held by circulation patterns that act like invisible basins. Once below the surface, plastics move with deep currents similar to sediment. They travel slowly along the seafloor, settling in depressions, accumulating in trenches, and collecting in areas where water movement weakens. These places mirror the behavior of natural materials, yet they preserve objects that resist decay. Plastic fragments persist where organic matter would dissolve or be consumed. Modern wreckage adds to this accumulation. Shipping lanes crossing the Atlantic carry not only cargo, but material that is gradually lost through wear, accidents, and disposal. Containers fall. Equipment detaches, paint flakes away. Over time, these losses form extended trails beneath frequently traveled routes. The seafloor below becomes marked by human passage, though the surface above reveals nothing. In deeper zones, lost cargo and fragmented plastics settle together. Nets, ropes, packaging, and synthetic fibers intertwine with sediment, forming layers that blend human material into the geological record. These materials alter the physical environment, creating new surfaces for organisms to colonize, while also introducing substances that do not belong to the ecosystem. The Atlantic traps debris because its circulation favors retention over release. Cold bottom water carries material slowly, limiting vertical mixing. Once particles reach depth, they remain there, shifting only gradually. Unlike coastal zones where tides and storms can redistribute waste, the deep Atlantic offers stability. Objects that arrive tend to stay. What lies beneath modern shipping lanes is not uniform. Some areas hold scattered debris, lightly dusting the sediment. Others show dense clusters, shaped by current patterns and seafloor topography. Valleys collect fragments, ridges deflect movement. The result is an uneven landscape where human material mirrors natural accumulation without ever becoming part of the natural cycle. This presence influences life quietly. Small organisms ingest microplastics mistaken for food. Larger species encounter synthetic materials that persist longer than expected. While the full consequences unfold slowly, the integration of plastic into deep ecosystems marks a shift in what the Atlantic carries within it. Yet this process lacks immediacy. Nothing collapses, nothing changes overnight. The Atlantic absorbs modern debris the same way it absorbs sediment, through patience and repetition. This gradual incorporation makes the problem less visible, but no less real. The ocean does not reject what enters it. It redistributes, settles, and preserves according to its own rules. In the darkness below shipping lanes, plastic does not announce itself as pollution. It becomes part of the background, mixed with wreckage and mineral grain. The Atlantic holds these traces without judgment, recording human presence in layers that will remain long after routes shift and vessels change. What sinks does not vanish. It finds a place within the Atlantic structure, resting beneath moving water, joining the quiet archive of a modern age written slowly into the seafloor. Salt water keeps its own record, written slowly into everything it touches. In the Atlantic, this record is chemical, patient, and relentless. Metal enters the ocean with strength and intention, shaped for endurance, yet the sea responds with quiet persistence. Salt dissolves certainty by encouraging reactions that continue long after motion has stopped. When steel settles into salt water, its surface becomes a meeting place between metal and chemistry. Salt acts as an electrolyte, allowing electrical exchanges that pull iron atoms away from their bonds. Oxygen dissolved in water joins the process, accelerating corrosion through steady interaction rather than force. The metal does not fail at once. It thins, weakens, and opens pathways for further change. This process unfolds differently across depths. In warmer, oxygen-rich water near the surface, corrosion advances quickly. Microorganisms assist by forming biofilms that alter local chemistry, creating microenvironments where metal breaks down faster. Paint peels, rivets loosen, plates separate. What was once rigid becomes porous. Deeper in the Atlantic, conditions change. Cold water slows chemical reactions. Oxygen levels drop. Currents move gently rather than aggressively. In these places, salt water still works, but it works more slowly. Metal persists longer, retaining form even as it transforms internally. Structures remain recognizable decades after sinking, preserved not by stasis, but by reduced pace. This difference explains why some wrecks last while others disappear. Longevity depends less on age than on environment. A ship resting in cold, deep water may hold its shape far longer than one lost closer to shore. The Atlantic offers both extremes, creating a range of outcomes that feel uneven when viewed without context. Saltwater also interacts with design. Alloys resist corrosion differently. Protective coatings delay exposure. Construction methods influence how water enters and spreads through a structure. Wrecks built with thick plates and limited openings slow the ocean's progress. Those with thinner materials or complex interiors invite faster intrusion, increasing surface area for chemical work. Sediment contributes to this memory. When metal becomes buried, contact with oxygen reduces further. Layers of mud and silt seal surfaces, limiting corrosion while introducing pressure. Buried sections may emerge decades later, still intact beneath a softened exterior. Exposure matters. What remains covered endures longer than what stands open. In contrast, wrecks exposed to shifting currents experience continual abrasion. Sand and debris scrape against surfaces, removing protective layers and revealing fresh metal beneath. Each pass resets the corrosion process, keeping it active. Over time, this movement erases sharp edges, collapses frameworks, and scatters components across the seabed. Some wrecks disappear not because they dissolve completely, but because they fragment beyond recognition. Pieces separate and spread, losing the outline that once identified them. What remains becomes part of the sea floor, metal grains mixed with sediment, indistinguishable from natural material at small scales. The Atlantic remembers all of this without intention. It records through interaction rather than observation. Saltwater does not choose what to preserve. It responds only to temperature, chemistry, and time. Where conditions slow its work, memory lingers in recognizable form. Where conditions accelerate it, memory diffuses into fragments. This long memory is uneven, but consistent in principle. Every object that enters the Atlantic begins a conversation with saltwater that ends only when material becomes part of the environment itself. Some conversations last centuries. Others conclude quietly, leaving no clear boundary between wreckage and seafloor. In this way, the Atlantic holds history without archive or order. Saltwater writes slowly, erases selectively, and preserves according to rules that ignore importance. What remains visible is not what mattered most, but what endured longest under chemistry and depth. The ocean remembers through survival, allowing some stories to linger while others dissolve into the background of time. From far above the Atlantic, satellites watch the surface with steady attention. They trace ship movements as small points of signal and light, translating motion into coordinates that update with each pass overhead. From this height, the ocean appears ordered, its traffic lanes clear, its vastness reduced to manageable grids. Technology suggests completeness, a sense that nothing crossing the surface can truly be lost. Tracking from space relies on cooperation between machines. Ships broadcast identification signals, satellites receive them, and systems assemble paths across digital maps. Radar senses large objects. Optical sensors capture reflected light. Together, these tools create a near-continuous picture of activity across the ocean's surface. For much of the Atlantic, this picture is accurate enough to inspire confidence. Yet gaps remain. Satellites do not watch constantly. They pass in intervals, leaving moments unobserved between sweeps. Signals depend on power, maintenance, and compliance. When equipment fails, is disabled, or becomes damaged, tracking weakens. The picture fades not all at once, but through small absences that add up over time. The ocean exploits these absences through scale and motion. Clouds obscure vision, storms scatter signals, waves break radar reflections into noise. In heavy weather, the surface becomes chaotic from above, reducing clarity precisely when ships are most vulnerable. Even advanced systems must interpret incomplete data, making assumptions that hold until conditions shift. The Atlantic also hides through depth. Satellites see surfaces, not interiors. When a vessel loses buoyancy, its transition from surface to subsurface happens quickly. Once below, it leaves the domain satellites are built to observe. The ocean absorbs it into layers of water that no orbiting instrument can penetrate directly. From space, the disappearance appears sudden, even when the process was gradual. Debris dispersal complicates recovery. Floating material may drift away from sinking points, carried by wind and current. What remains visible tells an incomplete story. Satellites detect fragments, but fragments do not mark exact locations. They widen the uncertainty rather than resolve it, spreading the search across expanding areas of water. Modern tracking also depends on prediction. Algorithms forecast movement based on past behavior, current patterns, and known physics. These predictions work well under stable conditions. In the Atlantic, stability is relative. Currents intersect. Weather reorganizes. Small deviations introduced early can grow as paths extend. What appears predictable becomes uncertain as distance increases. The Atlantic hides things because it is layered. Surface currents move one way, deeper flows move another. Winds shift independently of both. A ship drifting without power enters this layered system, its course shaped by which forces dominate at any given moment. Satellites capture snapshots of this motion, but continuity exists only through inference. There is also the matter of resolution. Satellites are designed to observe large-scale patterns efficiently. They are less effective at detecting small objects or subtle changes. A ship reduced to low profile, riding heavy seas, may fall below detection thresholds. In such cases, the ocean does not conceal actively. It simply exceeds the limits of observation. Despite these challenges, satellite tracking has transformed maritime awareness. Many losses that once vanished without trace now leave partial records. Paths are reconstructed, last positions are known, Yet the Atlantic continues to assert its complexity. It reminds observers that coverage does not equal control. What the ocean hides, it does so through interaction rather than intent. Motion rearranges evidence, depth removes visibility, time stretches uncertainty. Satellites provide perspective, but they operate at a distance that flattens detail. They see patterns better than moments. In this balance between observation and vastness, disappearance remains possible. Not because technology fails outright, but because the Atlantic is larger than any system designed to watch it. From space, the ocean looks contained. From within, it remains expansive, layered, and capable of absorbing what enters it beyond the reach of constant sight. The Atlantic gathers layers in a way few places do. History, science, and human movement overlap here so tightly that separation becomes difficult. Routes traced for trade later carried migration. Paths opened for exploration became corridors of industry and conflict. Each era left impressions that did not replace what came before, but settled alongside it, building a depth of meaning similar to the water itself. This overlap gives the Atlantic a sense of continuity. Events separated by centuries share the same space, connected by geography rather than time. Wooden hulls once crossed where steel later followed. Sails gave way to engines, yet the water beneath remained unchanged. What occurred above the surface varied, but the setting stayed constant, allowing memory to accumulate rather than disperse. Science deepens this effect. The Atlantic is younger than other oceans, still reshaping itself through slow geological motion. The seafloor grows and shifts. Currents reorganize heat across the planet. Weather systems are born and collapse here. These ongoing processes give the ocean a feeling of activity beneath apparent stillness. Change is constant, but rarely visible, sensed only through its consequences. Tragedy folds into this pattern without standing apart. Losses at sea often leave few physical traces, allowing stories to outnumber evidence. Ships vanish, signals end, wrecks remain unseen or incomplete. The absence becomes part of the narrative, encouraging retelling and reinterpretation. Over time, these stories layer themselves onto specific places, turning coordinates into symbols. So many stories come from the Atlantic because so many people have depended on it. It connects continents closely enough to invite crossing, yet remains wide enough to demand respect. It has been a boundary and a bridge at the same time. When success followed a voyage, the ocean faded quietly into background. When failure occurred, it became central, remembered as participant rather than setting. The Atlantic also resists simplification. Scientific explanations exist for its behavior, yet those explanations reveal complexity rather than closure. Currents interact unpredictably. Weather evolves rapidly. Depth conceals more than it reveals. Even as understanding improves, certainty remains partial. This balance between knowledge and uncertainty sustains fascination without resolving it. The feeling that the Atlantic is haunted emerges from this accumulation rather than from any single cause. The ocean holds evidence unevenly. Some wrecks remain visible, preserved in cold darkness. Others dissolve entirely. Some events are documented precisely. Others survive only through fragments of testimony. Presence and absence exist together, creating an atmosphere where memory feels incomplete. Sound contributes to this perception. The Atlantic carries noise across great distances. Waves, shifting ice, geological movement, and distant storms blend into low, persistent tones. These sounds have no clear source when heard in isolation, giving the impression of motion without origin. They reinforce the sense that activity continues unseen. Light behaves similarly. Surface calm contrasts sharply with depth, where darkness dominates. Sunlight fades quickly, leaving most of the ocean beyond direct vision. This contrast heightens awareness of what lies below, not as danger, but as distance. The mind fills what the eyes cannot reach. The Atlantic feels different because it operates simultaneously as pathway and barrier, archive and eraser. It carries stories forward while also softening their edges. It invites explanation without offering complete answers. Its scale allows countless human moments to occur without overwhelming the system itself. In this convergence of movement, memory, and ongoing change, the Atlantic becomes more than water. It becomes a place where meaning gathers naturally, not through intent, but through repetition. History passes over it, science studies it, tragedy sinks into it. Together, they create an atmosphere that lingers quietly, giving the ocean its distinct, resonant presence. The Atlantic keeps most of itself beyond reach. Even after centuries of travel, study, and observation, what has been seen remains a small portion of what exists. The surface gives an impression of familiarity, traced by routes and monitored by instruments. Yet below that thin boundary lies a volume so vast that complete knowledge becomes impractical. Depth stretches not only downward, but outward across time and distance. Much remains unseen because the ocean is structured in layers that resist easy access. Light fades quickly, pressure increases relentlessly, temperature drops and stabilizes. Each change limits how long observation can last and how closely it can occur. Instruments descend, record briefly, then return, carrying fragments of information rather than continuity. What is brought back offers insight, but never total presence. The Atlantic also remains dynamic at every scale. Currents shift gradually, the seafloor grows and settles, chemical balances evolve, life adapts quietly, mapping captures shapes that may already be changing. Measurements reflect moments rather than permanence. Understanding improves, yet certainty remains partial because the system never pauses long enough to be fully captured. The ocean resists being fully known because it operates without regard for observation. Processes unfold according to physics and chemistry, not visibility. Events occur whether recorded or not. A landslide may reshape the seabed without surface notice. A current may reroute materials slowly over decades. Life may flourish or fade far below any sensor. The Atlantic does not conceal actively. It simply continues. Scale reinforces this resistance. The distance between surface and floor exceeds what can be observed continuously. Even focused exploration leaves surrounding regions untouched. Knowledge grows in patches rather than across entire fields. Between surveyed zones lie expanses defined by inference. These gaps are not empty, only unvisited. This partial knowing contributes to the sense that the Atlantic feels alive. Motion never stops. Even when the surface appears calm, layers below continue their exchange. Water sinks and rises. Heat moves silently. Chemistry reshapes boundaries. Sound travels far and bends unpredictably. These constant adjustments give the ocean a presence that feels active rather than inert. Restlessness emerges from interaction rather than agitation. The Atlantic does not rush, but it never rests. Change happens slowly enough to escape notice, yet persistently enough to reshape outcomes. Routes that feel stable today shift over time. Patterns repeat without exact replication. The ocean expresses continuity through variation. The feeling of being watched arises from awareness of depth rather than intention. The Atlantic holds more than can be perceived at once. Darkness occupies most of its volume. When crossing its surface, the knowledge of what lies beneath becomes part of the experience, not as threat but as scale. Awareness replaces fear, distance replaces intimacy. What remains unseen is not a failure of effort, but a reflection of proportion. Human tools were built for land and air, environments where perspective is easier to maintain. Water removes reference points, absorbs light, and softens sound. It separates observer from subject by nature rather than design. Still, exploration continues. Each measurement adds clarity. Each descent reveals structure. Each survey narrows uncertainty without eliminating it. The Atlantic allows progress while preserving mystery. It accepts attention without yielding itself entirely. In this balance, the ocean keeps its secrets without secrecy. It remains open and closed at the same time, open to those who cross it, closed to complete understanding, alive through constant motion, restless through ongoing change, present in every measurement, yet always extending beyond what is known. The Atlantic does not ask to be solved. It exists as a system large enough to hold both knowledge and the absence of it. In that space between, curiosity endures quietly, carried forward like the water itself, moving steadily through depths that continue to shape, absorb, and remain.